Good morning again, and thank you for the introduction. Thank you for inviting me to COP conference. I'm Pedja Mihailovic. I'm coming from University of Belgrade, School of Electrical Engineering, and I'm going to talk about Faraday effect magnetometry. And I'm going to try to answer this question. Well, in the middle of the 19th century, Michael Faraday discovered that linearly polarized light will rotate its plane of polarization in the presence of magnetic field in some materials. The angle of rotation I'm going to call Faraday angle, and it's proportional to optical path length, a magnetic field component parallel to optical path, and Verde constant. Verde constant is a property of Faraday material. Today, we like to think of it as magnetic circular birefringence, since it's always proportional to difference in indexes of refraction of right and left circularly polarized modes. And you can see here that actually different velocities of circular modes through Faraday crystal are cause of this Faraday rotation. So if you can measure this Faraday angle, you can measure magnetic field or current that is inducing this field. So should we measure magnetic field in this way? Well, there are several advantages. First of these advantages is actually a fundamental one, because this is the only sensing method in which you don't have metals or semiconductors inside the magnetic field. The only thing inside the field you need is a Faraday crystal that can be dielectric and light. So you perturb magnetic field in the smallest fashion by this measurement. Another good thing is a frequency range. Time response of Faraday effect is in nanoseconds. So you basically have a frequency range that is limited by optoelectronic block frequency range. Also, measurement head can be small in dimensions, and you will see today that spatial resolution is already very good and can be further improved. The last advantage holds for all optical sensors, and information is carried by light. So no electromagnetic interference is a problem. The opposite is true when you are carrying information through copper wires. There are some obstacles also. I divided the obstacles in two categories: engineering obstacles and economic obstacles. First of all, Faraday rotation is small. For most of materials, it's beyond 1 degree for millitesla field range. So normalization of optical signal is mandatory. Also, Verde constant has complicated temperature dependence, so temperature compensation is necessary. Also, small Faraday angles means low sensitivity potentially, but I'm going to show you that with crystals with giant Faraday rotation, this can be significantly improved. And the last thing I am going to mention is that background radiation can influence normalization, so it has to be eliminated as well. On the other hand, optical components of necessary quality are still very expensive in comparison to electronic components. And that is a permanent problem. We are always trying to make our devices cost effective, but there are some components you just cannot exclude, like Faraday crystal itself. So where are we now, some 175 years after the discovery of Faraday effect in sensing? Well, one could say not very far, because there are not a lot of sensors based on Faraday effect in industry. On the other hand, there are a lot of papers and a lot of propositions for solving all mentioned problems. And actually all problems are individually solved, although there was a little effort to unite them into the single device. Well, one of examples is our fiber optic current sensor, and it is meant for for measurement of current in the power systems, so high currents. And we actually have a magnetic ring concentrator that can open and close the conductor, and you can see Faraday crystal here in the gap and the polarizers. So the idea of this magnetic concentrator is to increase modulation depth and to suppress influence of nearby conductors. Well, you can say that we lost a lot of advantages I claimed earlier, but note that we saved a high frequency range for power systems, and that was our goal for this sensor. So basically we can monitor first 25 harmonics, and that is sufficient for the power systems. But this sensor is also not in the wide use. So let's get back to engineering problems and solutions in order to show you how they all can be incorporated by holography. First about the normalization. The best method of normalization is delta over sigma normalization method, in which you actually divide the light beam into two orthogonal polarization linear states. And when you measure these states one by one, simultaneously but separately, you can determine the polarization state of an incoming beam, and you can measure the Faraday rotation angle. And if you set this angle to 45 degrees, so that is the optical quiescent point for maximum sensitivity, then you can see that voltages after transimpedance stages are given by these relations, and both beams depend on the light source intensity in the same way. So when you calculate angle by delta sigma normalization method, you actually lose light source intensity. So light source intensity fluctuations are not going to mask the signal. So this is a very good solution. But note that there are two possible problems. First of the problems is that you cannot actually compensate for different losses. One, you split the optical beam in two components. And the other problem is background light. If you have background light falling on the detector, it's going to disappear in difference, but it will not disappear in the sum. So basically, this background radiation is going to induce error in Faraday angle measurement. Well, you can say we are not going to have this in a fiber optic sensor, but eventual stray light will have the same effect. The other important question is the question of temperature dependence. If you find relative change of Faraday angle with temperature, you can see that it depends on relative change of crystal length with temperature. But actually this term here can be neglected, since it's 3 orders of magnitude lower than relative change of Faraday constant. And this term here is a consequence of heating the light source. If you don't have a light source on constant temperature, you will have a shift in wavelength, and Faraday constant is also wavelength dependent. So this term can be very high if you don't put temperature stabilized light source. But if you use temperature stabilized light source, you lose this term, and this relative dependence of Faraday angle reduces to relative dependence of Faraday constant with temperature. But that is not a very nice dependence. Actually, Verde constant in general consists of two parts. One part is the diamagnetic part, and the other part is paramagnetic part. This diamagnetic part exists in all materials, and it is consequence of Zeeman splitting, and it's approximately independent on temperature for not too low temperatures and not too high fields. And it also has a different spectral dependence in comparison to this paramagnetic part. This paramagnetic part originates in a spin-orbit interaction. It does not exist in the, diamagnetic materials, and it has and is inversely proportional to temperature. So altogether, dependence of Verde constant is complicated and a not very happy one for sensing. Well, but there are in the literature a lot of solutions for this problem. I'm going to single out 3 solutions that are superior to others. All these 3 solutions compensate for the temperature on the exactly same optical path as used for Faraday rotation measurement. First of them, I'm going to mention interferometry, and this is a very elegant solution where you actually monitor the crystal length change with the temperature, and from interferometric fringes phase, you conclude the temperature, and from visibility of the fringes, you determine Faraday rotation. This is a very elegant solution, but it's constrained to laboratory because it's very complex and it's very prone to vibrations. These 2 other solutions can actually be incorporated in a portable device. One also very good solution is interrogation at 2 wavelengths, and you are going to have 2 different Faraday rotations at 2 wavelengths, but they also depend on temperature on the different way. So actually their ratio is a function of temperature. So you can extract temperature from this ratio and then use correct Verde constant to determine magnetic field. And the third method was discovered by us basically because we used bismuth germanium oxide as a Faraday crystal, and bismuth germanium oxide possesses optical activity as well as Faraday rotation. And this optical activity is temperature dependent, so we use optical activity to determine temperature and then to use correct Verde constant to determine magnetic field. This solution can also be incorporated into a portable device, and I hope I can show you that with this picture. Here you can see measurement head that consists actually of 4 channels. One channel is input, and this channel is bringing the light to measurement head. And we have 2 channels in reflection and 1 channel in transmission. And I'm going to remind you that optical activity is a reciprocal effect, and Faraday rotation is non-reciprocal effect. So basically in these reflection channels, optical activity will cancel itself. And we can use these 2 channels to perform delta over sigma normalization, and we use this transmission channel to measure optical activity. Appropriate polarization states are made by thin polarizing films, so this measurement head can be very small in dimensions, actually dimensions of crystal, of Faraday crystal. The last question is a question of sensitivity, and on this slide you can see several Faraday materials and their Verde constant. Beside Verde constant, sensitivity is determined by magneto-optical quality of the crystal, and that is the ratio between Verde constant and the absorption coefficient. And among bulk materials, I singled out cadmium mangan telluride, which has a highest Verde constant of all bulk materials, and it depends on mangan share. And among other materials, I have to mention these materials that are reported in the literature that have giant Faraday rotations. Actually, those are thin films grown from liquid phase epitaxy on gadolinium gallium garnet. And I'm just going to single out this green one. I was lucky enough to get this crystal, and it really has amazing Verde constant of, you see, 24 million. But on the other hand, it can be only grown in thin films. So thickness of this crystal is 1 micrometer. So now I'm going to show you how holographic examination can unite all the good things about Faraday effect magnetometry and save the old advantages. Well, actually, we went into it with a different idea. Our idea was to measure Verde constant of cadmium mangan telluride at the whole surface of the crystal, not one point at a time. And here you actually see this 2 centimeter crystal in diameter that is illuminated with red helium neon light. And here is the digital camera. And we have one object beam that is passing through the crystal and a reference beam, and they overlap at the camera. And the crystal itself is in a magnetic field, and appropriate polarizations are set by polarizers. And on this slide, you can see the Faraday crystal, and you can see the defects. The high share of mangan creates defects, although it's increasing Verde constant. And after the reconstruction, you can see the hologram here. And of course, you can see imaginary and real part of the image. And since the crystal possesses defects, I'm going to show you results for 2 areas of the crystal. One is blue and the other is purple one. The blue one is a crystal without defects, and the purple one is on the place with defects. Well, as expected, the place without defects has a higher slope and has a lower measurement uncertainty. And this area corresponds to 21 by 21 pixels, and the area of crystal that corresponds to this area is 0.36 by 0.36 millimeters. So even here we have a very good spatial resolution for magnetic field measurement. So then we asked, so this went very well. We got what we wanted, and we asked ourselves, can we incorporate all these techniques in a holographic examination of Faraday effect? So can we incorporate delta sigma normalization, temperature compensation methods? Can we eliminate background light? So we went through a series of papers that was written by T. Columb, where he was discussing polarization sensitive digital holography. So we made this setup, and this is the setup I reported. So to have delta sigma normalization, you need 2 reference beams, and we have 2 reference beams and object beam overlapping at the camera surface. Actually, we found that this setup is not good enough. This setup has several problems. The difference in the optical path length of reference beams is too high, and it's very hard to adjust homogeneous illumination of camera surface. Actually, we don't use this setup. We went to the next setup in this moment of time. But I'm going to show you that, of course, with two reference beams, you get two pairs of images. And of course, it's more correct to reconstruct one image at a time. And then you have a problem of matching pixels to perform delta sigma normalization. In this moment, we use crystal defects to match pixels, and we got these results. Well, results are not very impressive, but these results can be significantly improved. And in this moment, we are actually on a more symmetric setup with two reference beams. I'm not going to go into the details of this setup because we are still working on it. One of the things we realized that we are using a camera with a rolling shutter. And that means that we are not measuring magnetic field at the same, at different pixels at the same time. So we are still working on improving this setup, and I hope we will publish results soon. Well, for the good part of the crystal, we got better results that we are sure will be even better when we finish this setup. And I want to, in the end, try to answer our question for the beginning. So what are the advantages of holographic examination of the Faraday effect? Well, it surely, we proved that it can ensure delta over sigma normalization. And note that you can filter out background light as a spatial DC component before hologram reconstruction. About the temperature compensation, that is something we didn't proven yet, but we see no obstacles to make simultaneously a hologram in, for example, green light, and to use two wavelength interrogation to do the temperature compensation. About the resolution, well, we are planning to use crystals with giant Faraday rotation, and we have a little drawback. Of course, camera noise is higher than noise of a photodiode, but we can, we think we are going to get to microtesla range. About the frequency range, note that all necessary informations are contained into one hologram. So basically, frequency range only depends on the camera frame rate. Well, that is good or bad news, because high-speed cameras are very expensive, and cheap cameras are barely sufficient to monitor 50 Hertz frequency. In the end, spatial resolution depends again on camera, pixel number and their dimensions, and of course on the quality of the Faraday crystal. But there is no doubt that this spatial resolution can be beyond a millimeter. So basically, with holographic examination, we can preserve all the advantages of Faraday effect magnetometry without losing any of them, and we can solve all the engineering problems that has to be solved. So basically, we think that answer to our question is yes. We have a lot of work in front of us to make a device that is portable. That is our goal in the beginning. So basically, we have to incorporate temperature compensation, and also you're thinking that we are not going to be able to make this as a portable device, but we think we will do that also when we design a reflective configuration. And the idea is to make a portable magnetic field scanner. And that is all for the time I have. So I want to thank you for your attention, and I'm ready to answer all your questions. Thank you.